In this video, we're going to begin to move past the abstract idea of a limit and start to narrow down a formal definition. So let's first look at a formal definition, a primary formal definition, and then we'll start to dissect it. So suppose a function f is defined for all x near a, except possibly at a. If f of x is arbitrarily close to L, and as close as what we may like or what we may choose, for all x sufficiently close but not equal to A, we write this little piece right here, and we say the limit of f of x approaches A is equal to L. All right, now you may be thinking I'm speaking a totally different language here, so let's break this down and see what this means. So let's go back to the beginning first. So we have just some function f. It doesn't matter what it is. We're just going to call it f. We can call it whatever we want. We just choose f. And there's some value a. Now this is a number, all right? We don't care what it is. It's some number. It could be 7, could be 8, could be 36 and a half. Okay, but it's just some number. And as long as f is defined for all the x values near a, but it doesn't have to be defined at a. So as long as our function is defined for the other values around it, then our conditions are met. And so that's the first piece. All right, but then if f of x is arbitrarily close to L, so now we're talking about the y value. So when we put an x value into f and it spits out a y value, if it's close to some value L, so keep in mind that this L corresponds to some y value, this A corresponds to some x value, and it just has to be close to L. It doesn't have to be exactly L. And we have this little provision in here as close to L as we like. Well, that's very subjective by nature, but it's going to be subjective, and that's okay. It needs to be close, relatively close. And that it's close to L for all sufficiently close x, but not equal to A. So all the x values that are close to A. So if our A is like 3, then we're talking about values like 2.99999 and 3.00001. So the x values that are really close to that value A, but not really there. Then this is what we define. We say that the function, as x approaches that value A, that function is approaching the value L. And let's look at it graphically to illustrate what we're talking about here. Okay, so let's say we have this function f of x, and it's graphed here, and it is a function, it passes the vertical line test. Okay, and we want to look at, well, let's just pick some value of 1, the x value of 1. And as we approach 1, so let's look at the left. If we're traveling along this curve, like it's a road, as we approach the marker of 1, we're coming up this curve and we're approaching a y value of 2. And as we approach from the other way, so say we're driving east on this road and we've got another person driving west on this road, and as they approach 1, well, what mark are they approaching? Well, they're also approaching 2. Okay, so the y value that we approach on both ends is 2, so we say that as x approaches 1, our function f of x approaches 2. Okay, and you might say, well, yeah, that's blatantly obvious. That's what it's defined as right there. If we just put 1 in for x, our function spits out 2. So we're not looking at anything significant here. So what's going on? Well, let's look at another point to illustrate what a limit is. Let's look at the x value of 2. So as x approaches 2, when we look at the left, so we're driving along this road headed east, we're getting closer and closer to an x value of 2, and what y value are we approaching? Well, we're approaching 3. And look at the same thing from the other side. As we get closer and closer to this x value of 2, we're approaching 3. So we say that as x approaches 2, f of x approaches 3. But you might say, wait a minute, what's going on here? We're defined up here at 5. F of 2 equals 5. So why didn't we say that f of x approaches 5? Because it doesn't. It's defined as 5. Yes, that's true that f of 2 does in fact equal 5. But that's not what we're talking about here. We're talking about the limit. We don't want to know what the definition is. If we wanted the definition, we just use the rule or use the graph and we could get it. This limit is talking about what does the graph approach as we approach a certain x value. And so in this graph, as we approach the x value of 2, our y value approaches 3. All right? And so even though we're defined somewhere else, we still approach this y value of 3. And looking at our last point that we're going to check out here is as x approaches 3. And you might say, well, our function isn't even defined at this point. And that's fine. If you remember in our definition, it doesn't have to be defined at that point. It just has to be defined at the points around that point. All right, so it just has to be defined at x values close to 3, not necessarily at 3. And so going with the same rationale as we approach the left and we approach the right, what's the y value we're approaching? Well, it's 4. So we say as x approaches 3, then f of x approaches 4. Now, let's look at this numerically. We could do this if we didn't have a graph and we were just given a function rule of f of x is equal to the square root of x minus 1, that quantity divided by the quantity of x minus 1. And if we plug this into a graphing calculator or plug it into any type of graphing utility and get a table as our x values get closer and closer to 1, so we've got 0.9 and then 0.99 and 0.999 and so on and so forth, as we get closer to 1, our y value is getting closer to a value of 0.5. And we check from the other end as well, as we get closer to 1 from above, so numbers up at 2 and getting down closer to 1, we also approach the value of 0.5. It's 0.499999875 and so on and so forth. And so we're approaching this value of 0.5. So what we would say here is that for this function, the limit of this function f of x as x approaches our value of 1 here is equal to 0.5, or we could even write it as 1/2, either way. So we know that we can't define this function at 1, because if we put in a 1, we get a 0 in the denominator, and that's a big no-no. So f of 1 does not exist, but the limit of f of x as x approaches to 1 does exist. And that's where we start to differentiate between where is a function defined and what is the function doing as it approaches a certain value. So this brings in the idea of a one-sided limit. And I've kind of illustrated one-sided limits for you here, talking about just a general limit. And with the one-sided, we have two different kinds, right-sided and left-sided, and they're just as simple as what they sound. One's coming from the right, one's coming from the left. And so when we're talking about right-sided limits, we're talking about x values greater than a. All right, when we're talking about left-sided, it's x values less than a. And we use a little notation. We say as x approaches a from the right, so we use a little plus. And as x approaches a from the left, so we use a little minus. And so these split things up and we have just one-sided limit. So we're going to use the one-sided limits to illustrate an error that most calculators and computer-generated graphs make. And so if you were to plug in this function right here of f of x equals x cubed minus 8 all over the quantity of 4 times the quantity of x minus 2, if you plug that into a graphing calculator or even a computer grapher, you're going to get a curve that looks like this. And there's an issue with that. As we can see, there's an x in the denominator, and putting an x value of 2 gives us a 0 in the denominator. So there should be a hole in the graph because our function is not defined at that point. So the real graph should look like this with a hole at the point 2, 3. Now what the calculator is doing, or what the computer is doing, is it's looking at the limit. It's looking at the right-handed limit. As we come from the right, f of x approaches 3, and as we come from the left, as x approaches 2, f of x still approaches 3, so it says, you know what? if it's approaching 3 from the right and left for all the values close, we're just going to define it at the point 2, 3, which isn't accurate, but that's why the calculator does that. The calculator is not just making a mistake. The calculator works on algorithmic processes that uses approximations and limits, and so it's going to define points when they shouldn't always necessarily be there. So we have to use our brain and realize that, hey, there should be a hole at x equals 2, so that would be at the point 2, 3. And we'll talk about how to evaluate the limits numerically when we have a function rule given to us, but we'll get to that later. One of the ways that we could do it is just making a table. Using a table, whether on the graphing calculator or doing it manually, we could look at values that are just a little bit less than 2 and values that are just a little bit greater than 2 and plug those into the function and see what we get. When we do that, we see that our functions approach a value of 3. What's significant is when these two one-sided limits are equal. And so when we have some function f and it's defined for x near a and all that, blah, 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 we say that the limit, just the two-sided limit of f of x as x approaches a, is equal to L as long as the one-sided limits are both equal to L. So as long as we get the right-handed side and the left-handed side agreeing on some value L, then we can say the two-sided limit is equal to L. Now, here's an example of one that does not agree. For instance, as we look at this function g, as we approach from the left, as our x values approach 2, we approach a y value of 4. But when we look at the right-handed limit, as we approach 2 from the right, our values approach 1. And so since those don't agree, we say that our limit does not exist. So our one-sided limit does exist. The limit from the left exists, it's 4. The limit from the right is 4, but the limit as x approaches 2 of g of x does not exist. Okay, so we have to be able to differentiate between the one-sided and two-sided. The one-sided limit is defined, it does exist, but the two-sided limit does not because the two one-sided limits do not coincide. Let's look at another possible error that we may make here. Let's say we have the function, just some function f of x is equal to cosine of 1 over x. And if we say, well, what happens, what is the limit as x approaches 0 of f of x? All right, and if we were to just to look at this number, well, that's close to 0, and 0.0001 is close, and 0.0001 is even closer, and oh, hey, look, we go from 0.5 to negative 0.95 to negative 0.9936. That looks like it's going to negative 1, but that's actually not correct. Because if we continue to investigate and see that, well, let's go even smaller, hey, we're up closer to positive 1, and we go even smaller still, we're back down to close to negative 1, and then even smaller still, we're negative just over a third. And so what's going on here? Well, if we look at the picture, what is this graph doing? Well, it's a cosine, so it's periodic in nature. But we also have an inverse function inside of a trig function, and so this periodic nature is continuing. It's just getting closer and closer and closer together. So the wavelength of each wave is getting smaller and smaller as x approaches 0 here, and so it oscillates back and forth. And even though there aren't any holes in this function other than the fact that we can't be defined at 0 because we get 1 over 0 inside of cosine, but other than that hole there, this function is defined everywhere else, but it's not approaching any point because it's oscillating back and forth. And so this is another example of where the limit does not exist. And so if we said the limit as x approaches 0 of this function cosine of 1 over x, well, that is equal to Nothing. We can't find it because it just oscillates back and forth and it never settles in on one value. So that's something we have to look out for. Certain functions can be a little tricky like that.